In the following videos, we're going to derive our finite element method using the principle of minimum potential energy. And in doing so, we're not going to really deal with the differential equations that are derived and model a two-dimensional or a three-dimensional object undergoing stress and deforming due to that stress. But I think it's important for you to understand that when you're using finite element analysis, you're solving differential equations. So even though we're not going to use the differential equations in our analysis, I'd like you to see what those differential equations are and where they come from. To that end, I'm going to derive or sketch out the derivation of differential equations or a system of differential equations that are actually the differential equations we're solving when we use finite element analysis on a 2D solid. To that end, I've drawn here a small cube or a small section of a two-dimensional object or an object we've modeled as two dimensions. To make things simpler, I'm going to say that any depth in the third dimension in the z direction has a depth of 1. So we can think of this as a solid object, a solid differential cube, if you will. And there are forces being applied to it. I have a force being applied at this face, Fx. There's a force applied at this face. This force has the value of Fx, and we're assuming that it's so small that any change is happening linearly. So the value here can be the force at this face plus the change in F with respect to x, and then this times this distance dx. There's also a shear force acting along this face, Fxy, and the force along this face is just simply Fxy plus df dy dy, the change, the distance in this direction. There's also a body force. This could be the weight of this cube, or it could be some other force acting throughout the volume of the cube. And since this cube's small, we'll assume this force is more or less constant. Because all of the areas on this cube are the same, I can rewrite the same expression in terms of stress. So here, the same thing. Now instead of Fx, I have the stress in the x direction, the stress plus the change in stress times the differential distance, the shear stress, again in the x direction, plus the differential change in shear times this distance here. Now, I'm only doing this for forces in the x direction. I'm going to get a differential equation. I could do this again in the y direction. That would give me a second differential equation. They're going to be very similar. I'm only going to do this in the x direction, and then I'll give you a final result, then show you what it would look like in the y direction. Okay? So what I'm going to do is I'm going to take this diagram and I'm going to sketch out for you Newton's second law. The sum of all the forces has to add up to 0 if this cube is not moving. So I have the sum of all forces in the x direction. I'm stating that must equal 0. And all I have to do is sum up these forces. Now, I've drawn these arrows going in the same direction, but obviously one of them, let's say this one, will make it go this way, and likewise we'll have this shear force going this way because they have to be opposing. So what I'll get is, now I'm looking at forces, again, the sum of all forces, this is the stress, so I have to multiply that by the area. The area in the z direction, we're just going to say is 1 to make things simpler. So what I'm going to get is, let's see, we'll call this positive and this negative. So we'll get Ex plus sigma x dx times this face here, which is dy dz. I'm saying dz is 0, so this is dy minus this stress, so dx times dy. I have my body force. Now this is a body force, So I have to multiply it by the area dx dy. I'll have plus x b dx dy. And then I have to deal with my shear forces. I'll have tau xy plus d tau dx, sorry, dy, dy. That's times this face dx minus what's going on here, which is tau xy dx. Again, all of this is equal to 0. Now, there's some simplification we can do, right? You'll see that I have a sigma x times dy, and I have minus sigma x dy. So these terms cancel out. Likewise, there should be a plus here. Likewise, these terms cancel out. Since this is multiplied by 0, some of these extra dy's I can get rid of. And I can rewrite this in a simpler form. D sigma x dx plus d tau xy dy plus xb equals 0. Had I done this in the y direction, I could also write d sigma y dy plus d tau xy dx plus yb equals 0. Now remember, these stresses relate to strain. Remember that I can find the stress dx is equal to some function of the various strain elements that we found, that we had in the last video. And I can relate that through that 3×3 equation with the D matrix. I'm not going to go over and do that, but I am going to just remind you that I have simple relationships where I can substitute in expressions that'll have Poisson's ratio and have Young's modulus, perhaps, and then be in terms of strain. So I can rewrite this equation, which is currently in the terms of stress, and I can rewrite this in terms of strain. And then I can remind myself that strain in the x direction is just du dx. Strain in the y direction is dv dy. And shear strain xy is du dy plus dv dx. Substituting in expressions for stress, for strain, and getting the appropriate Young's modulus or Poisson's ratio out of these terms, and then substituting stress, substituting in the derivatives in terms of u and x, I can rewrite these equations as the second derivative of u with respect to x plus the second derivative of u with respect to y is equal to 1 plus Poisson's ratio over 2 d squared u dy squared minus squared v dx dy. And for the other equation, the y equation, will give me d squared v dx squared plus d squared v dy squared is equal to 1 plus Poisson's ratio over 2 second derivative of v with respect to x squared minus d second derivative du dx dy. So this is a system, notice a system of two equations for two unknown displacements, functions of x and y, both displacement in the x direction, which is u, and displacement in the y direction, which is v. Okay? Now, again, we're not going to use this. This was just simply for your information, so you can understand that while we're solving for displacement in two dimensions, we are in fact solving this system of differential equations. We're not going to do that in this course, but you can derive the same finite element method we'll be using Galerkin's method and starting from these differential equations. We're not going to do that in this course, but I wanted you to see what these differential equations were.